Excellent.
Sorry for waiting. Let me start my presentation. Hello, everyone. My name is Changzeng, and I'm currently a assistant professor in Osaka University. So it's really my pleasure to share my recent study on the a controllable cross-gender voice conversion for social robots. And this study is caused by the Chaoran, Liu, Carlos, Ishi, and Hiroshi Ishiguro. So here's outline of my presentation. I will firstly introduce the introduction and related works, then go into some details about the purpose, method, experiment, and results. And I will draw a conclusion in the end of this presentation, and maybe we can discuss more about this study later in the QA section. So in this study, we're mainly focusing on build the voice for a robot to present personality and gender. So there are many conclusions can be drawn from psychological study, which is the voices are sometimes described as the ordinary faces. And we can understand this sentence as people rapidly make first expression of others and often based on the very little information, minimal exposure to our faces or the voices, and which is regarded as sufficient for humans to make up their mind about the personality of others. So as the figure shows here, we in our daily activity, we hear the voice of some others' utterance, and then we process this signal in our brain, and after that, we perceive which gender or which personality of this person is. And so in this slide, I put some advanced robotics in which we can generally categorize into two types based on the appearance. And the first one is the gender-specific social robots that basically are the Android robots, such as the HI, Gemini F, Erica, and HRP4C. And the other one is the gender-specific social robots that basically are humanoid robots. So there are a lot of different mechanical appearance of this type of robots, and we cannot tell the gender or personality from this type of robots. So basically all the personality expression or gender expression of these robots are based on the behavior and the utterance. And to prepare the utterance for the gender specific social robots is somehow straightforward, because gender and appearance are already fixed, and people can generally kind of stereotype of these robots, and so we just need to generate the utterance or the behavior that fit to this type of stereotype. So now we can use the phoneme-based text-to-speech method with the prepared phoneme database. And we can also prepare a database that to train a voice conversion model to convert the voice of speak 1 to speak 2, so that we just need to prepare one phoneme database of speaker 1, and then we can convert to any other type of people with our conversion model. However, if we consider the situation for the gender-free social robots, which will become more complex, and the voice is directly related to shaping the robot's gender and even their character. So this type of construction which should be different in different interaction cases. For example, like we use a robot to interact with children, we may need to equip the robot with somehow cute voice. But if we use this robot to interact with elderly people or adults or some other which is formal situation, we may need to have a voice that to make the voice become formal. So we need, in this case, prepare all type of the speaker level voice conversion, or the phoneme-based database is resource consuming and is even almost impossible. So we need a model that can be adjustable to give the robot a kind of ability to present different type of voice. So this is the key question that in this study we would like to investigate and solve. And in Controllable, there's some limitation of the recent voice conversion method. For example, the first one is very widely used sequence-to-sequence model. And this type of model needs the payload training data and most of the sequence-to-sequence model are not controllable. And the second one is the GAN general model, which is not require too much parallel data, and it can train on the non-parallel way. And currently, this type of model are successfully realized a speaker level conversion, but still, this type of model are not controllable. And in this study, we are mainly focusing on to make the GAN general model to become controllable in the cross-gender conversion. And here we highlight the we highlight our study. And in this study, we propose an intensity controllable model for voice conversion with the CycleGAN, and I use the transformer to enhance the temporal dependency and moreover to increase the controllability of the model. We add a condition embedding network as a controllable parameter. And then we propose a two-stage training procedure to realize the controllable conversion. And in the experiment, we evaluate the proposed method on the voice conversion challenge dataset and compare to two baselines. One is CycleGAN and one is Changzeng. So here is the flow of our method, which is a two-stage training dataset. In the first stage, we have a pre-training part. In this procedure, we use the self-supervised channeling to construct the voice from the same speaker. And the training is implemented on the multiple speakers so that the model can see as more as possible the voice from that generated by different speakers. And we have to mention that in this part, we set a condition as 0 to 0 or 1 to 1, which means that we tell the model that you have to construct the voice from female to female or male to male. And after that, we have a conversion part in which we fine-tune the pre-trained model on the paired speaker dataset. So in this part, the model was told to convert the voice from female to male or the male to female. So the condition becomes 0 to 1 or 1 to 0. And after that, it's testing. So we can use the condition as a scale to control the model's performance of the generating different speakers' voice. And this voice is controlled by the scale here to present how much percentage of the gender should be expressed. And here is the structure of a neural network model, a neural network. And for the spectrogram conversion, we use the convolutional layer and some normalization layer. And you can see that in the part that crop with the red framework is the novel design that we have in this study. One is the conditional embedding network, in which we input the condition and then it generates a kind of one-hot vector to control the model's conversion of the voice. And after that, we have a transformer here. And this module is supposed to enhance the temporal dependency of the model so that the continuity and naturalness of the voice can be enhanced with this module. And for the discriminator, is somehow straightforward. We just have a convolution layer and some activation functions. But for converting the F0 feature, because the F0 feature is just one vector, so it's somehow impossible to use a deep neural network to convert the F0 feature. So we just use the Gaussian normalization transforming to convert the F0 feature. But to increase the controllable of the F0 conversion, we also have a kind of scale value, the gamma here, to decide where is the target mean value. And then we use the Gaussian normalization transforming to convert the current voice to target voice. And here is the training loss that we designed for the model. And as you can see that in the left part is 3 types of the training loss that we have with the CycleGAN framework. The first one is cycle loss, in which we fit the generator A to B with the feature A, and we have a converted feature B. But because there's no there's no clear destination for the converter to convert feature B because we don't have parallel data. So we need to have a generator B to A to convert the feature B back to the feature A. And then we can compare loss between the original feature A and the reconstruct feature B, so that we have the cycle loss. The second one is the identity loss. So with this design, for example, we feed the generator B to A with a feature A. So in this pathway, the generator B to A have to recognize, oh, this feature is come from a speaker A, so we don't need to convert, and then we just directly give a reconstruct feature that of speaker A. So in this pathway, we compare the identity loss in the neural network model. And after that, there's adversarial loss, in which we have discriminator A and discriminator B to compare the difference between original sample and the reconstruct sample. And well, in general, we combine all these three types of loss as this formula shows. And in the training strategy, we somehow adjust the alpha and beta, which is a weight for the cycle loss and identity loss. In the algorithm I shows here, but maybe we don't have time to describe this algorithm. We just skip this. So our data set here is a voice conversion challenge, challenge data set, and we have two metrics. One is the mean opinion score, and the second one is the male spectrum distortion. And here is the result. As you can see that for the MCD and the male spectral distortion, we have a yeah, thank you so much. I will just quickly finish this. So in the CycleGAN scan out from all the other model, but we can see that even though we add one more function of the controllability, we still obtain somehow comparative result here. And for the mean opinion score, the proposed model have the same ability as the CycleGAN scan. And here is the speaker representations there. And we can see that in the middle is generated. The model with pre-training is somehow successfully to separate the speaker with different scale, but with the model without pre-training is somehow merged with each other. So here is the conclusion. I'll just skip this. And thank you so much for listening. And I welcome every of the questions and comments.